please let me start with my thanks to Kitty Panurgia and Christos Troussas and Claude Frasson and all the other participants today. Okay, good day everybody. This is the title of my talk. I will talk about, let's say, what I believe could be foundations, and the aphorism from stamp collecting to physics will be explained quickly later, even if it is something that maybe many of you do not know because there are no stamps anymore. But aphorism comes from the beginning of the 20th century when there were many stamps. So these are my affiliations. I'm currently still operating through our company that is called Digital Knowledge Technology Services in Milano, Italy. And I'm emeritus of the University of Montpellier, of the Laboratory of Informatics, Robotics, and Microelectronics of Montpellier. And I'm also, let's say, senior or distinguished fellow of the Foundation Bruno Kessler in Trento, Italy, that is rather well known for artificial intelligence. So this is the conference, and I'm very thankful to the organizers and the chairs for this invitation because, as you will see from my talk, the interest of this conference is not only that it is a new initiative, but also that it is an initiative that looks for me to be aiming at connections between, as it was said in the beginning, theory and practice. And this is, throughout my life, also my first goal. So a few years ago, I was invited to the Intelligent Tutoring Systems Conference in Zagreb, and I gave a talk about synergies between informatics and human learning with three main messages concerning my own work throughout the years: learner modeling, agents and services, and finally viewpoints, that is a more recent and still active research project. So what happened since 2016, since I gave that conference? Well, I'm just older and wiser, if you want, but in fact, it's not true, because that is not the only thing that happened. One more thing happened last year, and that is called ChatGPT, and all the cloud around this this product, this service, and this initiative. So when I was invited to NITS, I was thinking, well, maybe they didn't understand that I am not so active anymore since a few years. But then I looked into the tracks, and I found 3 tracks: track adaptive and personalized systems, track semantic and social web, track service science and software engineering. And then I looked, and I thought, it's interesting. Then I looked into the keywords of each of these tracks, and I thought, yeah, that is a fantastic stamp collection. Beautiful. For instance, recommender systems are in the track semantic and social web. And I thought, why are not they also in the adaptive and personalized systems? I mean, recommender systems are very, very personalized systems. Why are not they in the service science and software engineering track? So I thought to offer my own reflection about all these stamps, and this is my first summary that I will go over for you. first of all, I'll talk about the Rutherford aphorism and the nature of informatics, and the also link between interactive artificial intelligence and augmented intelligence with a few examples. Then I'll talk about my own work, and my own work will be revisited by trying to unify the three tracks of novel and intelligent digital systems by means of just three foundational concepts of interactive artificial intelligence. The concept of role in interaction, the concept of state, and the concept of collective intelligence. So I will try to talk about adaptive and personalized systems by means of my project in the 90s, NatLab. I'll talk about service science and software engineering by commenting about my own project or our own project, because each of these projects is a multi-partner effort. ELAGI, European Learning Grid Infrastructure of 2005. And finally, I'll talk about semantic and social web, and particularly collective wisdom from the Encore Encyclopédie Chimie Organique Électronique, the first attempt in 2005 to viewpoints that is the ongoing research project. So I'll try to link the three tracks with three foundational keywords: roles, state, and collective intelligence. Finally, I'll give a vision of the future about the motions, about deep learning and ChatGPT, about the integration of current modern, let's say, subsymbolic artificial intelligence with good old-fashioned artificial intelligence called hybrid artificial intelligence. And then I'll give, under request, particularly of Kitty, some words about ethics, and ethics in the sense of protection of privacy, protection of people from potential dangers of current modern advances in interactive artificial intelligence. And particularly, as you all know, the European Parliament is now discussing and approving a code that I will, let's say, challenge with another slightly different vision of the future of, let's say, legislation about products and services in artificial intelligence in particular, and computer science or informatics in general. So I'll go to the first summary and talk about a Rutherford aphorism, that is, all science is either physics or stamp collecting. Once more, people born recently even don't know what stamps were, but there were in the 20th century many people that collected stamps. And what did it mean to collect stamps? But to classify stamps according to some criteria. The problem with this classification is that the criteria are fuzzy, are unclear, and you can use different criteria to classify stamps. And just because stamps are not a science, there is no science of stamps. There is no science of stamps. There is science in physics, though. Why there is science in physics and not in stamps? Because, well, this is my version of Rutherford's aphorism. All science evolves from stamp collections to physics. And why it evolves? Because physics is the final goal, or physics, or the way a science like physics is structured, is the final goal of any scientific attempt. in the history. And what does it mean, that goal? To have a few foundational concepts, rules of combination, rules of abstraction, and then many consequences. If you look into physics, the foundational concepts of physics are very few, and you combine them and you find very many consequences. And this is what I would like to be the case for informatics as well. I'll show you further why. I'll give 3 examples. Some of you would know what Lisp is, Lisp processing, the language, computer language. It was invented and implemented in 1959-60 by McCarthy, and it was one of the most important computer languages for artificial intelligence. Well, it had Lisp in its final implementations, about 1,000 primitives, huge amount of primitives. Scheme was invented about 10 years later, and it was a fantastic change because, in fact, scheme consists of 6, 7, 8, maximum 8 primitives. Rules of combination, rules of abstraction, and many potential consequences. So in 10 years, the synthesis was huge, was very important. Nowadays, my preferred, let's say, language or computer language, you know, there are many thousands of computer languages, and one gets horrified by looking at all these languages, and one can say, what shall I do? How can I encompass, master all these languages in order to be able to, let's say, adapt to any problem? Because each language developed or discovered or developed has a particular goal. So in order to understand all this collection of stamps, I found Oz, the language Oz, I'll show you later, as the language that is a multi-paradigm language, a good synthesis of the foundational principles of all these stamps, all these different languages. If you want, there is another example historically, that is the evolution of biology. Biology was a kind of stamp collection till a couple of centuries ago. Trees or animals, there are animals left, animals right, there are mammals, there are birds, and sometimes fishes. Sometimes people made huge mistakes in the sense that dolphins are not fishes, they are mammals. And the point is the classification needs foundational principles. And of course, the principle of bearing the next generation, the children, is more important than the shape or where the animal lives. So happily, in the 20th century, the discovery of DNA, of the deoxynucleic acid, allowed to solve the problem and to understand that all species differ by a few components of DNA. So that's a historical example of a transition from, in inverted commas, stamp collecting to a really founded, well-founded, simplified, synthesized discipline such as modern biology. Finally, I'll give you also an example in tutoring systems, intelligent tutoring systems. In the beginning, there were many different ways of tutoring, many different stamps. But then people understood that, in fact, intelligent tutoring systems are for nothing else as learning, human learning. So tutoring is not the most important thing, but the most important thing of the process is learning. And learning is much more difficult, but once you understand the principles of learning, then you can tune the tutoring to the needs of learning. And then further, one more level of abstraction allowed us to understand that both tutoring and learning in interactive systems, human-computer systems or human-to-human systems, are all different examples of generic interaction. So the rules of learning and tutoring are a part of the rules for generic interaction. So you go to a level of synthesis and abstraction that is much higher as in the beginning. So I was telling you about Oz. Oz is an almost unknown language that I find the most beautiful language ever discovered and developed. Why? Because it's a multi-paradigm language. So you see here the principal programming paradigms, where you see on the top data structures only, on the bottom all different languages. There are maybe 50 or so, and maybe kind of some 30 concepts that you find here. The concept of record, which is the basis of anything. And then the concept of procedure. If you add records to procedures, you have first order functional programming. And if you have the notion of closure, you have functional programming. And if you don't have the notion of closure here, but you add the notion of cell and state, you have imperative programming. Pascal and C come from just these three little concepts: records, procedures, and state. And then you have all the rest. So you see call by need, synchronization, the threads, non-deterministic choice, and all the different languages that are, let's say, represented by a few foundational concepts. Do you still hear me?
Yes.
I hope. Am I too fast?
You're perfect.
Okay, thank you. Great. Okay. So let me give a manifesto before talking about details of what I believe informatics is about. Informatics for me is a science. It's not a piece of engineering. It's also a piece of engineering, but it's a science. And if you look into nature, you find essential properties like energy, matter, life, information. So these properties are respectively explored by physics, energy, chemistry, matter, biology, life, informatics, information. So information is the science of information in nature, in the whole of nature. So a natural science, like informatics, has the goal of understanding and forecasting natural phenomena, and informatics is the natural science that explores the transformations of information in nature. The engineering, all the rest of the engineering of artifacts, profits from and exploits any science. So informatics includes computer science, cognitive science, and artificial intelligence, and has two main origins: cybernetics, Norbert Wiener, control and communication in animals and machines, the notion of feedback, the notion of goal and of feedback, the physicist's inspiration. Example of, let's say, inspired threads or streams of research in this vein are robotics, interactive systems, agents. Then you have information theory, Shannon, same age, same time. The mathematics or statistics of codes, the mathematician's viewpoint. Now it's very popular with deep learning, for instance, and with connectionism and deep neural nets. It's a mathematician's, let's say, it's a probabilistic approach to the development of, let's say, forecasted properties, forecasted results. And then you have the huge vision of Turing that has to do with both with machines and meta machines. So interactive computers, as we are talking about, are not machines. This is a big misconception to consider interactive computers as machines. As Peter Wegner declared, wrote, and demonstrated, interaction machines are meta machines, are machines that produce other machines. So they're not to be unified, to be considered as traditional one-purpose machine, because they can generate new machines. So more of what are the artificial components, algorithms, databases, networks, that are all components. And cognitive science offers us the physiology of what are the natural functions: reasoning, perception, action, communication. So what is the goal of a system or of an animal, if you want? What is the purpose? What are the functions? And AI, artificial intelligence, is the link between natural and artificial systems. So the link between components and their physiology. That maybe allows to have a very simple and powerful, let's say, view of the difference between computer science, cognitive science, and artificial intelligence. Thing that I did not find, for instance, in the classification of ACM yesterday, when I looked into the 2012 last classification of ACM in what they call computer science. The Americans still keep this concept that is, for me, a little bit obsolete. Anyway, in case of doubt, in case you don't believe me that informatics is a science, that informatics concerns information in nature, think to the web. The web includes zillions of humans and artifacts connected. Humans are nature. Societies are part of nature. Think to the first studies on biological neural nets. For instance, Warren McCulloch, and first studies what the frog's eye tells the frog's brain, and so on and so on and so on. Think to the future Internet of Things, where interactions between chips, let's put it in this way, small computers, and people, and facts, and environment, and sensors, the sensors of any kind, will be so complex and so, let's say, multidimensional that one cannot consider that just an artifact. Think to bio-inspired computing. So information in nature, of course, informatics, current informatics, has to do mainly with its fantastic applications that everybody knows every day. What is artificial intelligence? Well, understand and forecast natural intelligence as a science, individual and collective. Of course, engineer intelligent systems and applications are side effects. My small remark, is there any intelligence that is not interactive? Are you able to conceive? Is it possible to have only algorithms, or in order to produce some intelligence? Or do you also always need some kind of interaction in order to, let's say, launch the algorithm and get and use and exploit the response and maybe give a feedback? So let me go to my own work and try to convince you that the three tracks of novel and intelligent digital systems, in fact, can be bound, linked, put in relation with each other by three or more than three, but a few foundational concepts. The concepts I chose are the concept of roles in interaction, of state, and of collective intelligence. So I'll talk to you about a first project in the 90s, NatLab, where roles in partner modeling and inverted dialogues were explored. About a second project, European Learning Grid Infrastructure in 2005, where stateful conversations for personalized services were explored, in particular services for learning, for human learning. And then finally, the final work from 2010 on that has to do about the transition between classical construction of ontologies, the project ENCORE, Encyclopédie Chimie Organique Électronique, where we tried for a couple of years, 3 years, to construct the basic ontology of an encyclopedia on organic chemistry without success, to the Viewpoints project that has capitalized on that experience to build a different way of constructing, let's say, repositories that can answer questions. So you'll find either in the DKTS website or in the NITS website a list of selected references about my own work that you can check yourself. In the NITS website are under the keynote speakers, and in the DKTS website are under my name. You'll find it. If you want, you can easily download each of them. So, the Natural Laboratory and Inverted Dialogues in the NatLab European Union project, what was it about? It was about, let's say, user modeling and the interactive construction of user models by dialogues. What is interesting is that today, I don't know how, because it would ask me to spend maybe 6 months in studying all the papers, but ChatGPT does a lot in this sense. So constructs during conversations a quite sensible partner model. At the time, the web was just in the beginning, and we envisaged to let interactive, let's say, processes allow the human to dialogue with the system, with the tutoring system, in order to extract and construct the model of the student by using different roles, exploiting different roles in this conversation. What is interesting is that this work that was applied to second language learning was later abstracted and generalized to any kind of interaction. So the paper in 1990 about the systems Nobile and Alice was about a particular specialization of the process of extracting and constructing user models. But then in 1994, the same, let's say, principles were considered to be valid and useful for any kind of interactive system in order to build, to construct progressively partners models. So here you see it's very simple. You see the workflow, let's say, initial domain representation, initial set of student models, extended set of student models, final set of student models by means of dialogue. And this is exactly the same workflow just for generic interactive systems. For instance, recommender systems, for instance, that need, of course, a human model or a partner model in order to recommend the right thing at the right moment. So knowledge acquisition and misconception representation are hard. We learned that. For instance, at the time, there were overlay models, but now the techniques are quite different. But this was declared and shown by John Self in 1990. Very, very good, very nicely. Perhaps today it is possible. For instance, crowdsourcing of partners models in ChatGPT is visible. I'm too old to tell you that in a year I'll understand exactly how ChatGPT works in order to tell you if I was right at the time or not. But what I'm sure is that the performance of ChatGPT in terms of personalization is incredible. Well, it's also true that the resources invested in the construction of that product and service are huge. we never will be able to compete with this kind of injection of resources. Anyway, the principles should be understandable. And if I would have a few years less, I would certainly investigate how they did it. So lessons learned from tutoring to learning. We learned that, of course, informal learning is hardly measurable. Only at the moment I've heard from my colleague that exploits the system viewpoints that we developed in the last 10 years, more than 10 years, that he apparently he was able to somehow measure informal learning. Of course, in the NATLA project, the roles of agents in generic dialogue were heavily exploited. So, in fact, in interactive systems, roles are crucial. That brought us in the beginning of the 90s to understand the interest of the pragmatics of languages, and particularly the theory of speech acts that has to do with roles, with goals, with understanding, and to develop the Strobe model for interactive agents. So let's go to this model that has to do with streams. So again, our attempts was to reduce the explosion of stamps, this explosion of different tricks, technologies, etc., to reduce them to a few foundational elements. And in the case of communicating agents, we reduced those agents to three concepts: the concept of stream, that represents the flow; the concept of object that represents the activity and the state, the algorithm managing the interactions and the state; and the notion of environment that, of course, represents, of course, the state. So what was interesting is that later this model was useful, if not crucial, to understand how grid services, namely stateful services, in the ELEGI project in 2005, could be represented by this kind of Strobe agents, and particularly containers in grid services that contain services and protect from intrusions, could be easily represented by Strobe environments. So Strobe was based on three concepts: the concept of object, to represent agents, to encapsulate state, and to do active message passing. The concept of stream, flow of messages. Now it seems that streams, everybody uses streams, but stream processing is something else. And it's quite powerful. So lazy evaluation for streams is also a kind of side effect for the notion of streams, exploitation of streams. The notion of environment to interpret messages. You have multiple environments because an environment in Strobe is dedicated to each partner in the conversation. And then, in fact, agents are considered as interpreters or as operating systems that have three first-class primitives, scheme primitives, and that undergo read, eval, print, listen loop. So it was a major simplification of the notion of agents that could represent functional, of course, functional applicative programming, intelligent tutoring systems and AI in education, and distributed AI and multi-agent systems. So what about services? Well, everybody knows that web services are stateless, grid services are stateful. So Agora that we built in 2005 represented stateful services by, let's say, orchestrating agents, groups, organizations, resources, and activities. And we also wrote a language that was called Agile, that integrated the Strobe agents with grid services. So this is an example of Agora. You see 4 windows and 3 small windows inside the windows. The Agora system in 2005 did the same, if not more and better, of what now we can see every day with Microsoft Teams or Zoom. You see here in the small window a video communication system flash meeting, and on the main windows totally different applications running in 4 or 5 different computers around the globe. In fact, this conversation was with Stanford University, and it was about the construction of an ontology in chemistry, and it was led by a person who wrote Protégé, so the main ontology language and interface that we knew at the time. So this is an old stuff that explains the 2 levels, the communication and the organization level of Agora. I'll go to the lessons learned because they are the only interesting ones. Functional model of multi-agent conversations, interactions, and dialogues. Cognitive environments are the base for partner modeling, and the foundations of virtualization of grid services. If you are not convinced about the interesting of stream processing, go to the streamreasoning.org website to see how different stream processing is from, and late and lazy evaluation are with respect to traditional eager evaluation and list processing. Anyway, all that emerged from the analysis of, let's say, tutoring dialogues or learning dialogues. So state is not just cookies. This is something I don't understand. People get crazy about cookies, but having sharing states is much more powerful. Of course, it's heavier. But you need history. And I wonder what ChatGPT does. I'm not sure it does just cookies. Anyway, Agora was a protected environment. We addressed the same problem of protection and sovereignty in viewpoints. And generic mixed initiative dialogues are possible. mixed initiative was a buzzword invented in 1970 by Jane Carbonell about in his first paper on artificial intelligence in computer-assisted instruction. Mixed initiative dialogues completely revolutionated the history of, let's say, tutoring systems and interactive systems. And then we learned that services are not products because services are evaluated by the consumer of the service and not by the producer, not only by the producer, like often it is the case of products. Viewpoints. Viewpoints has to do with knowledge construction and exploitation, and there are 4 primitives in viewpoints: agents, topics, documents, and viewpoints. And viewpoints is a, let's say, research project that has to do with the construction of knowledge and the access to that knowledge construct, but in a collective way. And by exploiting not the notion of logic, but the notion of proximity of resources, dynamically updated in a knowledge graph. I've heard that finally viewpoints, the application has allowed to produce a measure of collective informal learning. Viewpoints. So, in order to build knowledge on top of the big data, we need the viewpoints from people we trust. So that's one point. So we need people we trust. So we build knowledge not with anyone, but with the people we trust. Trust and learning have to do with semantic proximity. For instance, see Vygotsky, who taught us that learning occurs by adding new concepts to concepts that are proximal. One single connection is enough to bridge the gap between 2 separate views on a shared reality. Let me go to an example that says most of what I want to say. So there is a need. I need information about electronic virtual money. And then there is a scenario where you have, of course, people around you, agents that give advice, give recommendation if you want. Pete, George, Henry. And each of these people that are in this scenario gives a different kind of recommendation. Give the recommendation to look into documents, give a recommendation to look into different keywords, different topics. So in fact, the word is reduced to documents, topics, and agents. Of course, these are human agents, but there are also artificial agents. For instance, the agent latitude and longitude that gives you the coordinates of where you are. That's a very simple agent. But there are other agents today. For instance, ChatGPT, that is also an agent. It's also a service or an agent, an active element. So agents consist of human and, in viewpoints, humans and artificial agents. And they help each other, they interact to build collective knowledge. There is a formalism, but I will not present you the formalism because it's too late. It's every time the same kind of links and notes. This is important. What is a viewpoint in this formalism where you have several knowledge resources, namely agents, documents, topics, and people deposit different viewpoints that link each viewpoint links two knowledge resources. So an agent to an agent to a topic, an agent to a document to another document, a document to a topic, two documents with each other. So this operation of generating a viewpoint is an operation that is only done by active agents, so human agents or artificial agents. And the viewpoint is just a link that has a strength, theta, and a time, tau. So then you construct a knowledge graph that is a bipartite graph that contains resources, so agents, documents, and topics, and viewpoints emitted by active resources, these agents, human or artificial, that link with a certain strength and a certain time, each two resources. But then it's not the only thing. Let's say, biologically inspired, if you want, mission of viewpoints is to, let's say, construct a different graph that we called knowledge map, that for each couple of resources, you see here, R1, resource 1 and resource 2, collects all the viewpoints or the bindings that have been emitted connecting these two resources into a single one, and the operation is done continuously, permanently by the system by means of a map-reduce operation, typical stream kind of behavior or algorithm, in order to build between each couple of resources a synapse, what we call a synapse, and this is the bio-inspiration. Synapses are continuously built so that you pass from the knowledge graph, which is, let's say, very cold, to a knowledge map, which is much more linked to the choice you make. This is an example of, I will speed up because I wanted to give time for questions. I will speed up as much as possible. An example of, on the right bottom, you find the knowledge map. On the left top, you find the knowledge graph. In the center, you find the perspective that gives to different kind of viewpoints a different weight. Then you have a search, the keyword Francesco Di Castri, which is an agent, represents the search. Then you have another example of the application that allows you to visualize a document by simply clicking on the preview. And then you have an example of how the same knowledge graph with the same kind of components of, let's say, with the same anatomy, set of resources, set of viewpoints, by tuning different perspectives, that is, by giving more or less weight to different connections, allows to have different knowledge maps. This tuning is important because you do not attribute the same weight to an agent that emitted viewpoints, an agent that you do not trust or you trust less, with respect to an agent that you trust a lot because it's one of your inspiring colleagues, for instance. So in this way, you tune your knowledge map with respect to other interferences, and you capitalize from the social behavior of your colleagues that are in the community. So again, you find a few references. Let me go to the end of the story. Okay. Emotions. By emotions, I just know quite good the visionary work of Claude Verso about emotions, and emotional intelligence has been under-evaluated. It's extremely important, and we envisage within viewpoints to introduce emotions as one of the factors that enhances or reduces the distance between knowledge resources, agents, documents, or topics. Personality traits. We studied personality traits in the beginning of the 2000 with Guta Nunes, Maria Augusta Silveira Neto Nunes, that has done a lot of work on personality traits. Another quite ancient student, one of the first students, Paolo Vesani, does a lot about neuroinformatics. And so I think the three issues will be crucial in the future. What about deep learning? Well, it's normal that a stochastic approach or a probabilistic approach, let's say, gets weight with respect to traditional logic-based approaches like semantic web and all the other ones. So approximation and probability is a science, is part of mathematics, and is very, very, very important. You never have knowledge that is certain, except in mathematics, where you have, of course, the foundations are invented. But in reality, you never have certainty in anything, and nature is very, very probabilistic. So, large language models, but again, the symbols win. And interestingly, ChatGPT combines many, many of those issues into one single melting pot. Why? Because it links large language models, or symbols, with probability, with deep learning, let's say algorithm or processes, and with prompting. So it means capitalizing from adaptation and learning of the system by the interaction with the user. So ChatGPT is one of many different applications that are currently being developed because its foundations are quite powerful. Of course, more and more, also ChatGPT is an example of integration with between the probabilistic word and the symbolic, or the subsymbolic word and the symbolic word, but integration with good old-fashioned AI, so neurosymbolic integration and hybrid artificial intelligence is important, is very, very important. We started to be interested with that in 1988, but it never went on because at the time there were other priorities. Let me end this story. I've asked too much time to you. I'll leave a few minutes for questions. Well, ethics. Ethics, for me, start from the assertion that computers are not just machines. So you can't treat the development of informatics, of computers, of networks, as if those would be machines of the 19th century. These are not just machines, because they are meta machines. They're machines that throughout different zillions of interactions produce other machines. There is a Science and Technology International Advisory Board at the European Union, where my president, Gianna Martinengo, is a member of, and she presented a few months ago, long before the AI Act that is now being discussed and probably approved was conceived and produced. And there were two things in this advice that I think are the foundation of a good, let's say, protecting ethical behavior with respect to the new developments in AI and computing in general. First statement, AI and software systems should be considered as individual collective drugs because benefits and dangers are on the human receivers of services, not on systems behavior resulting from its anatomy, for instance, algorithms, or physiology, for instance, consumers' goals. So the tendency to class computer systems in terms of components or in terms of goals is a wrong tendency because those systems interact and they produce new systems all the time. So what is important is to look into the effects on the consumers, on the users, individual users and collective users. So for us, for her, the new software life cycle requires an assessment delegated to a European authority, exactly as it is the case of drugs, exactly as it is the case of the European Medical Medicine Agency. The assessment should be based on regulatory sandboxes, evidence-based experiences, as are clinical trials for EMA, for the European Medicine Agency. So those are two principles that I wanted to quote because at the moment people are very afraid of the development of AI in particular and computing systems in general. So I've now let the audience thank you for your attention.